Okay, this is our video here, live video today, on the power function, the hyperbola, and it's 1 over x graph. Okay, so we haven't looked at these much before. These graphs show asymptotic behaviour. Wow, what a term that is, asymptotic behaviour. Have you, ladies and gentlemen, looked before about or done anything with asymptotes? Yes? No? Hold on, let's get a firm commitment here. Who's heard or used asymptotes before? Yes? No. Rightio, mixtures. Let's start from scratch. Asymptotes are lines on a graph for which that graph or that function is not defined. And this is the first graph that we looked at this year. And in fact, there's some details about asymptotes. Line on a graph, it's usually dotted, dashed. Okay, so it's easily visible. The function is not defined at that point. And 1 over x, this graph has a vertical asymptote at x equals 0 and a horizontal asymptote y equals 0. Now, why is that? Because this graph can't be defined at those values. If I look at y equals 1 over x, if x is 0, we get 1 over 0. Now, you should know by now that we can't divide through by 0. We can divide 0 by something, but we can't divide through by 0. Therefore, when x equals 0, y is undefined. Okay, so this graph, and vice versa is the case here. So this graph doesn't have any values for x when y is 0, and doesn't have any values for y when x is 0. So how do you put that on a graph? Okay, you mark it with an asymptote. Now, for the pure graph of 1 over x, which I'll reveal in a moment, can't actually see the asymptotes because they're the same as the axes. But later on, we'll denote them with dotted lines. So what does a graph of 1 over x actually look like? Well, I can see people furiously taking notes. I'll just pause just for a few seconds. So here's the graph of 1 over x. That's what it looks like. And for a nice neat one, I copied and pasted that from another site. But you can see there that graph doesn't cross those axes. So y equals 0 and x equals 0 are asymptotes. Y equals 0 is the vertical asymptote, VA for short. X equals 0 is the horizontal asymptote, HA for short. So those two, the two sections of the graph will never touch the axes. They'll get closer and closer and closer and closer all the time, but they'll never actually touch them. Now obviously x is 1, y is 1, because if x is 1, you get 1 over 1, which is 1. That's why the points 1, 1 are there. If x was 2, okay, you get y equaling 1 over 2. So if x is 2, so it'd be about there somewhere, okay, y would equal a half. Whoops. That point there, you get 2 comma a half. And similarly, if x was a half, you'd get 1 over a half, which would be 2. So when x is a half, y equals 2. Like so. And you get values down here in the bottom left-hand corner for when x is negative. So that's the basic shape, those two sections for 1 over x. Now, my not so neat diagram graphs are drawn here, but same sort of dilations here. In the bottom corner there you can see y equals 2 over x. Sorry, the trial thing blanks it out a bit. But if you get y equals 2 over x, the graph is dilated by a factor of 2 from the x-axis. So that 2 down there, that's a dilation factor. So if it was 3 over x, it'd be dilated by a factor of 3. It'd be even further out there somewhere. Okay. So you can get dilations with these as well. The higher the number on the top there in the numerator position, the further it is dilated away from the x-axis. You can see there, 1, 1 has become 1, 2. And we looked at dilations this morning, that first exercise we did. Because it's dilated from a factor of 2 from the x-axis, that point is taken double the distance away to 1, 2. Same with all points. Haven't drawn it very well, but you can get the idea. Okay, what about negative 1 over x? Actually, before we do that one, let's look at that one. So 0.5 over x, okay, a number between 0 and 1, would take the graph closer to the x-axis. So that dilation there be dilated by a factor of 0.5 or a half from the x-axis. So in a sense, taken closer to the x-axis, because 1, 1 becomes 1.5. If x is 1, if I put x equals 1 in there, 0.5 over 1 is 0.5. So a number higher than 1 takes it away from the axis. A number between 0 and 1 takes it closer to the axis. Back a step. So here we've got y equals negative 1 over x, and that's reflected it in the x-axis. You can see that the blue graph here, in effect, it's also reflected in the y as well, but we'll just not confuse things. So the bottom bit, it's taken to the bottom. So any point here is reflected down here, and any point here is reflected up here. So it's reflection in the x-axis. That's negative 1 over x. The two bits go the other way. Did that one? Now you can get reflections in the y-axis as well. And I'll cover two things here. In fact, we'll come back to that one. I just want to show you the shifts first. So let's look at this. Now you can see a -3. Same things come up every time, don't they? You know, with the quadratics and the cubics, a -3 is taking it to the right. Same here, a -3 on the bottom in the denominator takes the graph to the right. Now you can see for the first time I've got that asymptote there. Okay, that's the horizontal asymptote, which usually is the axis, the y-axis, but it's been moved 3 places to the right. Okay, so the horizontal asymptote is now, and this is important because you can get confused, x equals 3. And you can see the black graph, the whole graph's been shifted 3 places to the right. Going back a step, same graph, and you can see though, but here at the bottom, if you've got negative x minus 3 there, that actually reflects that 1 over x minus 3 graph in the y-axis. So it's taken it and reflected in the y. So a negative in the denominator there reflects in the y-axis. A negative up here reflects in the x-axis. Right, up and down shifts, pink graph there. This time we've got our vertical asymptote's the same, but our horizontal asymptote has moved. It's moved up 2 places. So our horizontal asymptote here is y equals 2. Okay, it's been moved up 2 places. And the whole graph has been shifted up 2 places. So once again, a number out by itself, same thing, same principles, moves the graph up or down. So you can see there the combination of transformations. The dilation factor, the left-right shift, the up-down shift from the original graph. The original graph sits on the axis, the graphs can then be moved. Okay, let's look at an example. State the changes that would be made in order to the graph of y equals 1 over x, the standard one, to obtain the graph of negative 4 over x plus 2 minus 1. Okay, so we don't have to draw this, we just have to state the transformations. Okay, so here it is. Now, remember our order? We start with dilations. What's our dilation factor here and by how much and in the direction of what axis? All details, please, for dilations. Somebody? Hadush? Yeah, now, that's really important because the negative is not relevant to the dilation. It's the number itself. Okay? So we don't talk negative dilations yet. So it's dilated by a factor of 4 from the x-axis. So it'll be taken away big time from the x-axis. All right. That deals with the 4. Now let's deal with the fact that it's negative 4. What is that going to do? Bethany? In the... Good. Reflection in the x-axis. All right. That's dealt with and that's dealt with. Now let's move down to the plus 2. What's what's the plus 2 going to do on the bottom? Somebody? Yep, Alistair?
Translate.
Yep. Translates graph 2 units to the left. Good. It's a plus 2. What about the negative 1 out by itself? Hadush?
40 units down.
Yeah. There we go. There's our translations for that one. We don't have to draw it, but that's just a start. And this sometimes see standard exam questions which just ask you to do that. They give you an equation like that and say, okay, in order, what are the translations, transformations? All right, now, a couple more different things here. And we are going to actually draw a quick sketch of this, just to see what's going on. So, here's the question. For the graph y equals 2 over x minus 3 plus 2, state the equations of the asymptotes, the domain and the range. Alrighty. Let's just put that there. Let's just draw a quick sketch of this, see what it looks like. Oops. Put a solid line in, I think. Okay, so let's get our axes going. Where's our asymptote going to be, or asymptotes? What is the minus 3 going to do to the graph? Don?
3 to the right.
Yep, so we're going to have an asymptote here. Good. What about the plus 2? Where's that going to take the graph? Daniel?
Up 2.
Yep. So there's our axes. So it's going to look something like this. There's no reflections. There's also a dilation, so it's sort of slightly further away than it usually would be. We don't have to worry about the intercepts here, so it's just a general shape. So that's something like what the graph will look like. Okay, top right, bottom left, with our vertical asymptote is x equals 3. Our horizontal asymptote is y equals 2. Now, so we've answered that first question. That's the equations of the asymptotes. That's done. The domain. Okay. Now, when we do this graph, because it keeps on going forever and ever that way and up there and down there, so it's going to cover all real numbers for x except for what? 3. Okay? That's the only value of x it won't cover. It'll keep on going that way. It'll keep on going that way. Now, if I drew it to its fullest extent, okay, it'll cover all x values, but it won't cover. So we put a backslash, a set bracket, and we put the number 3. So that terminology tells me that x will cover all real numbers except for 3. Now let's look at the range. Okay, so remember the graph keeps on going that way, keeps on going that way, keeps on going that way, keeps on going that way. What y values will it cover? Up and down. What y values will it cover? Will?
All of them.
Except for?
2.
Excellent. So real numbers except for 2. So there's our domain and range. Okay? Example 3. Right, sketch the graph now of y equals 2 over x plus 2 minus 4, showing the intercepts with the axes and the position of the asymptotes. Alrighty. Let's have a look at this. A few extra bits there, which I'll just cross out. Here's a graph that we want to draw. Now, hint, I might write this on the recording. Hint, draw rough sketch first. Okay, because, well, we'll see why. So what I'm going to do first up is just see what this graph's going to look like before I find my intercepts. I've done it again. It's just a rough sketch. See what it's going to look like. Where the asymptote's going to be, guys? Madush? 4 down, okay, yep.
And
To the left, well done. Okay, there's our asymptotes. It's to the left, 4 down. So it's going to be something like this. Alright, something like that. Now the reason I do that is that I want to see if there's going to be X and Y intercepts. Because you can imagine a graph. I'll just digress for a moment. You can imagine a graph that might look something like this. Let's change colour for the asymptotes. And that. Okay, so something like that. There. Yeah, there and there. So you had a graph like that. Alright? Now I know that graph has got a y-intercept and an x-intercept. So I know what I'm looking for and I know roughly where they are. So when I'm finding my answers here, I know that if I don't get a value out here somewhere and I don't get a value up there somewhere, something's wrong. So I've got a rough idea of my values. Okay? So I haven't got a calculator for these. So I sort of know what I'm doing if I do a rough sketch first. I also know whether I have to find an x or y-intercept or not, because some of these cannot have x-intercepts. Okay, if they're translated downwards or whatever, sometimes they can lack x-intercepts. But I'll get back to it later. But it gives you a rough idea of what we're looking for. So there it is, a rough sketch. All right. Now let's try and find the x and y-intercept. So we'll just copy our thing over again. Okay, so same method as normal. How do we find an x-intercept? In general? Like y equals 0. So let's do that. X plus 2 minus 4. Next step would be to take the minus 4 across. So we get 4 equals 2 over x plus 2. Times the 4 by x plus 2. We get 4x plus 8 equals 2. 4x equals 2 take 8, which is negative 6. X equals negative 6 on 4, which is negative 3 on 2. Okay. So our x value is negative 3 on 2. That's looking all right. Okay, because I know that that one there is negative 2. So negative 3 on 2 looks about right. Advantage of the rough sketch. All right? We're pretty much on track, we think. Now, let's have a look at our y-intercept. And remember, that's negative 4 there, so we're expecting our y-intercept to sort of be negative 3-ish, somewhere around there. Let's see what we get. To find x-intercept, to find y-intercept, we make x equals 0. So y equals 2 over 0 plus 2 minus 4. Y equals 2 over 2 minus 4. That equals 1 minus 4 is negative 3. So our y-intercept is 0, negative 3. Once again, that fits in with our rough sketch prediction at about negative 3. Alright, so we're ready to draw this graph. So we've got negative 3 on 2, those two there. So we'll draw it up nicely now. Oops, run out of slides. What I might do is go back here and just do it here now. That we've finished it up. So, good sketch now. Axes. And asymptotes. So, we are over here at neg 2 and neg 4. Our intercept here was neg 3 on 2. and here was neg 3. So our graph's going to be something like this, and like this, over there. Label y and x-axis. Now I haven't worried too much about the dilation, but that's what our graph would look like. How's that? Alright, let's label our asymptotes, should do that. So that's y equals neg 4 and x equals neg 2. Righty, now I was talking with Ashley about this before, about finding equations of graphs and general principles of how to do it. Okay? So here's an unknown graph, and our general formula is a over x minus b plus c. What do you notice about it? Its shape compared to the, you might have only just started doing these, so let's just go back and remind ourselves way back on the first slide somewhere. There it is. What do you notice about the graph we're about to look at? It's reflected, okay. So that will mean that the value of a will be negative. We don't have to worry about that, but you know, when we come to find a, we must remember that it's going to be negative. All right, so what's going to be here? Where's the graph being shifted from the standard one? How many places to the right? 2. So what? X take 2, you're on to it, Alice. Okay, so that's going to be x take 2. So we're going to be having y equals mystery number over x take 2. What's our c? Plus 3. Okay, what points have we got? We've got 0, 6 and 4, 0. 0, 6 and 4, 0 are the 2 points we've got. Okay, let's copy some of that over to the next slide. And we'll get started. If you wish. Okay, so let's get rid of some of that other stuff. Oops. A bit small. Anyway, I thought I'd just copy that background stuff, because now we'll look at it in more detail. So, the situation we've got is y equals a over x minus b plus c. And we know that it's going to be negative 2 on the bottom because it's gone 2 places to the right. And we know it's going to be plus 3 because it's gone 3 places up. How do we find a? We use one of our points. Okay, so which point should we use? What do you think? Yep.
Can you use any of them?
Yeah, I'm going to use 0, 6. I think. Because I think 4, 0 could be a problem. Anyway, we'll just use 0, 6. So, y equals 6 equals a over 0 minus 2. See how, Ashley, it's the same method? Okay? Get the points you know and then find a point to find the unknown. So 6 equals a on neg 2 plus 3. We take 3 from the left, we get 3 equals a on neg 2. A will equal neg 6. So as we predicted, because the graph's reflected, a has been a negative number. So our graph will be y equals negative 6 on x minus 2 plus 3. How's that? Alright, so there's an introduction to the hyperbola, and we're now starting now, maybe a couple, 7 minutes to go, but definitely for homework. I haven't got any videos to watch for homework, and we've got a few days. I might set one towards the end of the period, because I don't think we've got maths now till Wednesday, do we? No? So exercise 2C, let's get started.